to Lecture 1-4, an Interactive PID Controller Design. In this lecture, we will build an Interactive PID Control Design tool in Python. However, you need not install Python to try the design tool, although I do always recommend that you install Python and use it. It's a great tool. This tutorial is available at the following web page. So go ahead and click this button to launch the notebook in your browser, which will look something like this. In a moment, we're going to scroll to the bottom of that web page to interact with the PID gains that update the closed loop step response. But what we're doing here is for the unity feedback block diagram, figure 1-6, so this is the block diagram of the control system we're designing with, we will design a PID controller for this controller block C. Design requirements are A, less than 20% overshoot. So we don't want to overshoot the final value by more than 20%, or we want to do it less than 20%. B, an initial peak in less than 0.2 seconds. So we want to have that first peak happen in less than 0.2 of a second. And C, steady state error for a step response being 0. Okay, so we want the final value to approach 1 for a unit step response. We say the command is 1, the output should be 1 in steady state. So those are our design requirements. We don't have all the analytic tools that we need, but we do have the ability to create some simulations with a closed loop transfer function and tweak the PID controller gains sort of as we wish. So what we'll do is we'll first load some packages. So NumPy, SymPy, the control systems package for Python. Matplotlib for doing plots, and then this is for some display stuff, IPython display, for when you're using a Jupyter notebook. This is for doing widgets. So this interactive plot that we're going to create, where we can change the controller gains, resimulate, and show the step response, requires this IPyWidgets package, Python package. So we'll start out with some symbolic transfer functions. So we define some symbolic variables here. So S, KP, KI, and KD for the 3 PID gains. S for the Laplace transform variable. And we're going to start out symbolically. So we say, here's the plant, here's G. So if we go back to our block diagram, this is the plant transfer function. And we want to use the controller with its gains that we get to decide to affect how this closed loop system responds to our step command. So here's a pretty printed version of the transfer function. The controller has the following symbolic transfer function. So we know it's a proportional term plus an integral term plus a derivative term with the appropriate gains, and a pretty printed version of that. The closed loop transfer function for the unity feedback system is as follows. This equation is something that we derived a couple lectures ago when we looked at the closed loop transfer function. So it was for unity feedback, so the equation was CG over 1 plus CGH. But for unity feedback, H is 1. So we have this transfer function. We simplify it using the symbolic simplifier. And then this is another simplification bit here. This isn't strictly necessary, but I wanted to print out the closed loop transfer function symbolically in a way that was a little bit prettier. So what I did is I split the numerator and denominator using the fraction function, and then I ran a map which runs a function on each element of a list. So in this case the numerator and denominator, what I'll do is, using a lambda function, I'll take the element and I'll run the collect function on it, the SymPy collect function. I'll collect in term s, which is the Laplace transform variable, and then I'll transform that map into a list. So we've got a list, and then I'm just going to take the two terms from the list and assign them to t numerator and t denominator. And then in the symbolic, I redefine t sim to be the numerator over the denominator there, and I display it here. So that's the closed loop transfer function with the proportional, derivative, and integral gains in there appropriately. And as you can see, as we change those gains, it changes the closed loop transfer function significantly. It changes the poles, changes the zeros. So it's definitely going to change the step response significantly as we change those gains. So that's just what we want. So we have these symbolic representations, which aren't strictly required in a lot of cases. So a symbolic representation of a transfer function is something that is helpful to have, but it is also something that is sometimes more easily skipped if you want to go right to the control Python package representation of a transfer function. So if you don't want to start with symbolics, see what the closed loop transfer function would look like symbolically, you can always skip right to the control transfer. But if you've got a symbolic representation, as we would frequently want to do, and you would like to convert that to a control transfer function, there's no easy way to do that. So I wrote this little conversion routine here, this function called sim2tf. And what it does is it takes in a symbolic representation of a transfer function, and whatever the Laplace transform s variable is that's used in that representation, and it turns that into, and through a little bit of a sleight of hand here, it turns that into a control toolbox transfer function. So it's a bit of a hack, but it does work. Whenever you use this exec function, there's always a sign that there's a hack going on. So this isn't super smooth, but it does work. Note that the tf sim, which is one of the inputs here, must have no symbolic variables besides s_var, the Laplace s. We can apply this to gsim then, but not to csim. So csim has kp, ki, and kd in it, 3 symbolic variables, and those when we convert this to a control toolbox transfer function, we can't have any symbolic variables left in it. So other than s, which is not the only one in csim. So let's just try it out on gsim. So the plant, which is all numerical besides the symbolic s's, we do sim2tf, and then we look at what the type is. This is how to tell what type of object you're working with in Python, and it returns a control transfer function object. So we've done it successfully. We've created this routine. So now, defining the closed loop function. We need to create a function that specifies the gains, substitutes them into the symbolic closed loop transfer function, then converts it to a control package transfer function object via sim2tf. So we'll make this function called PID_CLTF, takes in a closed loop symbolic transfer function and the 3 gains. By default, each of the gains, kp, ki, and kd, will be set to 0. So we use symbolic kp, ki, and kd in here, and inside the routine we have to say that s is a transfer function s. Then we take the symbolic transfer function and we substitute in for the symbolic variables these numerical kp values that come in with the routine. So that's using the subs method of a symbolic object, a SymPy symbolic object. And then we return the substituted in closed loop transfer function so that it's only numerical other than the symbolic s's. We give that to sim to tf with the s representing the transfer function. Laplace transform variable to that function, return that. So we should get out the closed loop transfer function as a control transfer function object with the gains put in appropriately. So let's just, for instance, look at what happens if we say Kp is 1, Ki and Kd are 0. We could do that by just plugging the symbolic closed loop transfer function in with Kp equals 1 to that function we just created and then displaying the output in a pretty printing, and sure enough, it looks like a nice transfer function. So now we can use the control package's step response function, which is very nice, to get a step response for a single set of gains. So let's set our gains to be Kp2, Ki1, Kd 0.1, and we can pass those gains then to the PID CLTF function with the symbolics, with the symbolic closed loop transfer function tsim. And that'll give us a closed loop transfer function that is ready to operate on with the step response. That'll give us a closed loop transfer function that will be ready to operate on with the step response function here. So we define an array of time values. So using linspace from the NumPy package. From 0 to 3 seconds, 200 values. And the control toolbox's step response function, you give it the transfer function object, and then you give it the time array. It returns the time array and the step response. So then we can simply plot it. This opens up a figure, creates a set of axes on it, plots on those axes the time and the step response, labels those axes, and then shows it. And the outputting figure there is given here. So step response. Notice the command is 1, so it's hopefully going to end up here. Looks like it will. It looks like that integrator is kicking in here, but it's just slow to kick in. That steady state error is getting smaller here. And we have an initial response too slow for what our design requirements are. We want to get in 0.2 seconds, which is like here. We want that first peak to happen. That didn't happen. It doesn't overshoot at all, but we probably want to have less than 20% overshoot is what the spec said. So we probably want to be close to that. So we want to be up here. So with those gains, it wasn't what we wanted. The design isn't working, but we saw how to go through the mechanics of simulating the step response. So for a different set of gains, hopefully we'll get what we want. But we have 3 knobs to turn here. And so when you have 3 knobs to turn, that's a lot of different possible things to try. Sometimes you can get away with using a widget like this to just tune the gain. So this creates a little widget which essentially does the same thing in a loop. So the description of it's here. So this interactive step response looks like this. So we set the PID gains using the PID CLTF like we did above, and we simulate with the step response like we did above, and we plot it. But what we do is we take the GUI interaction callback function update, and we use that to set the new gains. Then we simulate it, and then we replace the old line on the plot. So we do that in this sort of interactive loop, and this is the code for it here, and this is what we get for a response when we've got these gains. So we take the 3 sliders here, we move them around, and this is what we ended up with. So let's do this interactively now in the web browser. you can click on this link at the top of the lecture, like we mentioned at the top here. So go ahead and click the link, and that'll take you to the following website. So at first, it's going to spend a little bit of time loading in this GitHub repository where this Jupyter notebook lives. And so it'll take a moment to load. And once it does, it'll load in this notebook. So this is a Jupyter notebook with code cells that are written in Python, but you can also get Jupyter notebooks to work with other languages. Python is the language that the Jupyter notebook was written for, though. So we can take this notebook, we can execute code cells individually. Shift Enter will allow us to do that. So we could Shift Enter our way down here. Notice that the code cells are interspersed with Markdown cells. So if you look here, these are written in Markdown. This is a header in Markdown. And it renders to some some visual that isn't too bad to look at here. So, and I also will turn off those so it even looks a little bit nicer. So what we can do is we can just go through, Shift Enter our way down, or we could hit Cell, Run All, and it'll run all the cells. But let's just Shift Enter our way down. We see all the stuff that we did in the lecture. The symbolics are happening here. We define the transfer function. We define these variables, or we define the PID CLTF to transform it from symbolic to a transfer function object in closed loop with the gains inserted. We display one possible closed loop transfer function with gains inserted, and we're going to plot one example. So here we go. That's what it looks like. This is actually an interactive plot, so you can zoom in here if you'd like. It's pretty cool. And then once you're done with that, continue on down to the widget. Shift Enter on that, and it will create this, which I want to get all on one page here. So I'm zoom out slightly. Okay, so what we've got is the closed loop step response for PID controller with proportional gain 1, integral gain 0, and derivative gain 0. So it's just a gain controller at this point. And what the step response is doing is it's the output response to a unit step command. So we're saying the command here says go to 1, and the step response is going to like 0.5. So it's doing, the final value is incorrect. So we have steady state error of like 50%, right? That's not good. And it also is too slow. We want to have this peak in less than 0.2 seconds, which this is taking over half a second, so 0.56 seconds to peak. So we're going to want to increase these gains. So we start sliding things around. If you increase the proportional gain, notice that it gets a little bit better in steady state error. So as we increase it, it is going to go towards 1, but it does it with a lot of oscillation. As we keep increasing, the oscillation increases, and there's going to be a crossover point here where it becomes unstable. You can see that happen around 0.55 or so. So even if you drop that KP back down so that the steady state error is significant, remember we're trying to go to 1 here. If we increase that integral gain, we'll see that steady state error improve. So that's nice. We see that it's going to 1. The higher we make Ki, the faster it goes to 1, which is not always going to happen with every plant, but it does happen frequently. And then we have this speed problem, right? The speed problem, we need to peak by about 0.2 seconds, and it's still around 0.5. So the Kp and the Ki haven't really helped with that at all, but we hope the derivative will help. And sure enough, the derivative does help. The peak happens earlier and earlier the larger we make this. It does create this sort of low wiggle. So we don't peak above the steady state value of 1 that we're headed for. We peak below that. And if we increase that proportional gain again, that'll improve. So something like that. 20% overshoot is what we were aiming for. So we don't want to go above 1.2 with this peak. We're a little bit above that right here. So we could try seeing how these other parameters affect it. Lowering Ki helped it a little bit, but we'll see. We know if we lower Kp, it'll help. If we lower Kd, it doesn't really affect it that much. Well, let's actually up Kd a little bit. We need to get that peak to happen in 0.2 seconds. We're there now. And so that 0.19 seconds it takes, under 0.2 seconds to peak. But we are about 4% over on overshoot. So let's drop the Kp down just a little. There. So now we're at 16% overshoot. Pretty good. Pretty good. And our, when we peak in 190 milliseconds, I guess. So yeah, so that's pretty good. So this design would work. So this Kp, Ki, and Kd would work. Obviously, this is not the ideal way to design a controller, just sliding around variables until we get a step response that we like, but it is a way. So as a sort of quick and dirty way to start doing PID controller design, this is one way to go. So this is available on in the text. Click that button and you'll go to this website. It'll launch this interactive repository. So and you can always change, if you'd like, what the plant is. So you could change the plant dynamics, and then you could tune again for your new plant. So something to play with and have a good time with. So yeah, hope you enjoy it, and see you next time.